Alright, so in this video I'm gonna be explaining another important article with the title Unpaired Image-to-Image Translation Using Cycle Consistent Adversarial Networks. So at the first sight you may wonder, how is it going to be relevant to this domain adaptation? But at the end of this video, if you think about it, you will see that it could be very relevant to domain adaptation, and in future videos you will see even how exactly they are related to domain adaptation. So this paper in 2020, you see, given any two unordered image collections X and Y, our algorithm learns to automatically translate an image from one into the other. For example, we want to go from Monet drawings, Monet paintings to the photo. So we can have a function that translates it from Monet to photos. Or from zebras, you can translate any zebra to a horse. And this figure shows paired training data on the left. Consists of course, this article is also useful for domain generalization in the case that your target is unseen during training. So paired training data is on the left, consists of training examples where the correspondence between X sub I and Y sub I exists. With that, consider unpaired training data consisting of a source set and a target set with no information provided as to which X sub I matches which Y sub J. Image-to-image translation is a class of vision and graphics problem where the goal is to learn the mapping between an input image and an output image using a training set of aligned image pairs. You can also extend it to natural language, that you translate one sentence to another sentence. So let's carry on. However, for many tasks, pairing training data will not be available. We present an approach for learning to translate an image from a source domain X to a target domain Y in the absence of paired examples. Our goal is to learn a mapping G such that the distribution of images from G of X is indistinguishable from the distribution Y using an adversarial loss. Because this mapping is highly under constraint, we couple it with an inverse mapping from Y to X. So this is our mapping, but our inverse is F. The forward is G. So that F of G, as you see, is just X. F of G of X is just X. You see, F of G of X is just X again. So our model contains two mappings, and their associated adversarial discriminators D sub Y and D sub X. To further regularize the mapping, we introduce two cycle consistency losses that capture the intuition that if we translate from one domain to the other and back again, we should arrive at where we started. Forward cycle consistency loss and backward cycle consistency loss. So the idea of using transitivity as a way to regularize structured data has a long history. In visual tracking, enforcing simple feed-forward, backward consistency has been a standard tricks for decades. In language domain, verifying and improving translation via back translation and reconciliation is a technique used by human translators. So neural style transfer is another way to perform image-to-image translation. These are related works, which synthesizes a novel image by combining the content of one image with the style of another image. So our goal is to learn mapping functions between the two domains, X and Y. Our model includes two mapping, as I said, F and G, where D sub X, we have two discriminators as well. D sub X, discriminator for X to distinguish between X and the translated images. The same way we have discriminated for Y, aims to discriminate between Y and G of X. So we have our objective contains two types of terms: adversarial losses for matching the distribution of generated images to the data distribution in the target domain, and cycle consistency losses to prevent the learned mapping G and F from contradicting each other. So we incentivize this behavior using a cycle consistency loss. F of G of X should be X. And again, the opposite should be true. G of F of Y should be Y. So this is very clear. You see the input images and the output images. So we go from this to this. Isn't it interesting? So we go from photos to Cézanne, who is a great painter. And then we go from horses to the zebras, winter to the summer. We can change it. And then if you do reconciliation, this is almost the same as the original one. Of course, it's a little bit different, but almost the same. So the full objective is that we use GANs 2 times and then the cycle consistency. And this lambda hyperparameter controls the relative importance of two objectives. So we apply 2 techniques. We replace negative log likelihood by least square loss. This loss is more stable during training and generates higher quality results. In particular, for a GAN loss, we train the G to minimize E and train the D to minimize E. Second, to reduce model oscillation, we follow this article and update the discriminator using a history of generated images rather than ones produced by the latest generators.